Okay, good morning, everyone. I think we have to start now. This is our assignment 1, and it's due, I think, in a few days. We should just finish it and submit maybe by Monday. So there's question 1. There's question 2. There's question 3. Last time we met, we actually discussed, I think, 3.1, 3.2, 3.3, 3.4. We also discussed yes. I think we are now on error correction model. That's what we want to do. So we're gonna quickly do it. I will just introduce some stuff quickly, then we go straight to it and try to get our solutions. So we are starting now. Maybe let's start by having this document. Are you seeing the PDF I'm sharing?
Yes.
Okay, great. This is what we want to look at today. Today we want to look at your people are still joining in. Today we want to look at ECM, diagnostic checks and modeling, and we'll be done with this. So thank you so much for joining me. This is some of the things that we discussed last time we met. That was the long run period. What is a long run period in econometrics? And we say that it implies that variables have converged upon some long-term values and are no longer changing. So this is what we also looked at last time. And we said you can also even have XT here, XT of current period, if it's equal to XT of the previous period, if it's equal to XT of the last 2 years. If these are equal, they are converging, right, upon some long-term values. So we can safely say here is equal to XT star, or you can use just X. If you see the variables converging upon some long-term values and they are no longer changing, you should know that we are now in the long run, right? That's why if you look here, we then drop the subscript. If we write it like this, it means we are now in the long run. There's no subscript, right? This is what we looked at last time we met. And I also want you to remember that when we are running the long run equation, we run it with the level data. So if you remember, our long run equation was something like this. Our long run was something like YT is equal, say, beta 1 plus beta 2 XT plus maybe the error term. We are running with the people are still joining in. We are actually running with level data. But if we are to look at the short run, you see that in the short run, we can see that our values are still changing. So there is the change in YT. This can actually be something like this, plus the error term. We should know that you are in the short run if you have something like this, right? But in the long run, if you look at, but if you check in the long run, you see that the change in YT is equal to 0, because YT of this period is equal to YT of last period. So if YT of this period is 10, for example, and the YT of last period is 10, 10 minus 10 is 0. So in the long run, you see that the change in variables is just equal to 0. Let's say you are having 2 variables, YT and XT, you see that the changes will just be equal to 0 in the long run. But in the short run, you see that, let me write it like this. You see that in the short run, but in the short run, you see that the change in YT is some value. It's actually maybe greater than 0, right? It's some value. It's not equal to 0. Let me write it like this. So it could be negative, right? We should know that when we are in the short run, the change in YT is not equal to 0, right? So this is what we want to do today, and see why should we run regressions for the short run? Why should we do that? Why do we need that? We also want to check if there are some significant relationships between variables in the short run. Yes, we ran our long run equation. That was when we tested for co-integration, right? And we discovered, we actually saw that there was a relationship, right? What about in the short run? Are there any significant relationships in the short run? That's what we want to do. So you see that we'll move on to our ECM, and ECM is very important. Why is it important? Obviously, it will help us in finding the relationships between variables in the short run. So why is it important? Why is the ECM important? It is important because it can help us, let me say it is important because it can help us find relationships between variables in the short run. It actually helps in finding relationships between variables in the short run, right? And it's also important because it can actually help us in checking whether the model is capable of adjusting to its long run equilibrium after facing some shock. There is a shock, right? Maybe our variable is below its equilibrium value. Will it be able to go back to its long run value? Will it be able? And if it's able, how long will it take for it to go back to its equilibrium value? Guys, are you there?
Yes.
Yes.
Okay. I want you to get this one. Why? Because you shall see as we move on to our e-views doing our ECM, constructing our ECM there, you will see that there's need to do some interpretations. And you really have to understand some of the theory before we move on to e-views. So I am saying the ECM is very important, guys. Why is it important? I have two reasons here. The first reason, it actually helps in finding the relationships between variables in the short run, whether the variables have significant relationships in the short run or not. And how do you check whether variables have significant relationships? I know you know of your T statistics. We're going to be looking at the T statistics and say, indeed, these variables in the short run, they have a significant relationship. So we're going to be looking at the T statistic of the ECM. You shall see that, right? And the other reason why ECM is important, we're saying it helps in checking whether the model is capable to adjust to its long run equilibrium. Helping in checking what? Let me just write it. You'll get these notes when I'm done. Helping in checking whether the model is capable to adjust to its long run equilibrium after facing some shock. After facing some shock, right? So how do we check that? Just how are we going to do it in views? We're going to run, yes, the ECM. We have our ECM there. The results are there. We're actually going to copy from eViews. We paste it on our Word document. But how then are we going to be able to check whether the model is capable to adjust to its long run equilibrium after facing some shock? How are we going to do that? How? Right? So that's what you want to learn. So when you go there, it's much easier. Okay, let's move on. So guys, from the long run, sorry, let me do this. We are saying that we now know the long run equation, how it looks like. Actually, the long run equation, we run it with level data. But what about the short run? We are saying the short run, how do we write it? Obvious is change in YT, please follow now, is equal to some constant plus say beta 2 change in XT plus the error term. Let me change the color here. I want you to see something. If you look at the short run, there's a change here. How do we get a change in YT? If we're in this period, if I'm to ask who wants to try, how do we get the change in YT? Obviously, we know if you want to see the change, look at the YT of this period, then subtract the YT value from previous period. This is the change in YT. This is the difference. This is actually DYT. Are we together there?
Yes.
Yes, 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 we are.
Oh, great. Same with this one. If you look at this one, how do you get this? It's actually XT, the value of X this period minus what it was last period. This is the change in XT, which is actually the XT, the D. You can even put like this, right? I want you to follow here. I really want you to follow. If you look closely at our short run equation, you can see that it's in difference. So in your ECM, you shall see that you are going to have some variables that are differenced, right? So basically what we are saying here is when we want to come up with our ECM, what is it all about? What is this ECM all about? It's very important to know. What is it all about, this ECM? What is it all about? You will see that if you look at the ECM, it's actually bringing together, you are going to bring together short run and long run components in this equation. How then do you bring the long run component? Because if I go back here, if you look at this short run equation, maybe let me change the color. If you look at this short run equation, you will see that it's only having short run components, right? Oh, sorry for that. Let me keep on admitting people here. We can actually see that here, oh, this is not a good color. You can actually see that we are having our short run components here. We're having our short run components. But when we are now building an ECM, we are bringing together short run components and long run components. Obviously, long run components, they are not different like this. Remember when we ran our long run equation, we did it in levels. But if you look at this one, equation that I'm having, it's just showing the short run components. So let's try to bring together the two, short run components and long run components. How do we do it? So we have a way, according to Engel and Granger. How do we do it? This is how we should do it. I want to come up with the ECM. How do we do it? Please follow. You have something like this. Change in YT. You have change in YT. This is the short run component. Is equal to, say, beta 1, our constant, plus beta 2 change in XT. This is also a short run component. Now let's bring in the long run component. We know that our long run equation, right, was something like this. YT is equal to beta 1 plus beta 2x plus the error term, right? This was the long run equation. And from this equation, we know that we came up with our residuals. We came up with our residuals, if you remember, right? And our residuals, in my case, it was res underscore LOV. So if you bring in the residuals here, you actually bring in the long run components. So you see, we are going to add, let me change the color so that you see, we're going to add something like this, beta 3 residuals. But these residuals are legged ones. Then after that, we say plus the error term, right? So if you see an equation like this, if you see an equation like this, right, you should know that this is an ECM. Why? Because it's an equation that is bringing in both short run and long run components together. Why are we doing that? We are doing that because once we have an ECM, it will actually help us in finding the relationship between variables in the short run, right? Are there any significant relationship in the short run of the variables we are dealing with? It will also going to help us whether the model is capable to adjust to its long run equilibrium after facing some shock. So what I want you to see from this before we go to our views, please be patient, is this part, maybe black, is this part. We said ECM can help us with two things. The first one, it can help us in finding the relationship between variables in the short run. In other words, whether the variables have significant relationships or not. So you can even check the relationship between X and Y. This is in the short run, and see if there's any significant relationship or not. So after running, we are going to check the T statistics, and we know statistics, we know our rules of thumb. If the T is greater than 2, you conclude that there is a significant relationship. We are going to do that. This is the other part for 1. What about for 2? Was the other important, the other importance of ECM is it helps us in checking whether the model is capable to adjust to its long run equilibrium after facing some shock. How do we do that? We are going to be guided by this part, right? And here I want you to listen and listen good. Here, there's this beta 3. This beta 3 you are seeing here is the coefficient of residuals or the legged residuals. This beta 3. So for you to see whether the model is capable to adjust to its long run equilibrium after facing some shock, you should be in a, you should actually look at your beta 3 there. If your beta 3 is significant, right, then you know that, oh, so this model I'm having, if there's a shock in the short run, it can actually go back to equilibrium after some time. But how long will it take to get back to equilibrium? You're also guided by this beta 3, because we know this beta 3 should be bounded. it should be between -1 and 0, right? And why is it negative? I think we have a question. It should always be negative. And why should it be negative? Let's say, sorry for that. Let's say, guys, are you still there?
Yes, Prof.
Yes, we are.
Yeah.
Let me use VAT. Maybe in the long run, the VAT collection we are going to be dealing with, let me just take a figure like 1,000. This is the long run value. It will not change. Maybe in 2023, it will be 1,000. In 2024, 1,000. 2025, 1,000. It means you are now in the long run, if it's not changing. But when you are in the short run, this VAT will be changing, right? Let's say there's a shock. So I will deviate from equilibrium or the steady state path. Let's say the VAT is above by maybe it's 1,200. It's just a shock. So it's above the long run value, right? Are we gonna be able to go? Is it gonna be able to go back to its long run value after a shock? If it's going to be able to go back to the long run value, how long will it take to go back to the long run value? What is it that will determine whether this model will be able to go back to its long run equilibrium after facing some shock? I am saying make use of beta 3 that we are having there on our model. We are having beta 3. This beta 3 is what we are going to look at. And we are saying this beta 3 should be negative and should be bounded -1 and 0. Why should it be negative? That was the question. We are saying if it's above and if this one is negative, obviously it will be pulled back to 1,000 if it's negative. If it's below, say it's 900, there's a negative here of 100, right? That's the difference. If it's negative, a negative and a negative, it's a positive. So it will be taken back to the equilibrium. So it should always be negative. It's above, if it's negative, if the coefficient is negative, it will pull it back to equilibrium. If it's below, in other words, if it's negative, if you multiply negative and negative, it will be a positive and it will be taken back or taken up to equilibrium. In other words, we are simply saying here, oh, my pen. It's something like this. If this is the steady state path or the long run path, and if it's below here, it means it's a negative something. If it's above here, it means it's a positive something. So for you to take it back to the steady state, you need this one, you need to take it back. This one, you need to take it up. So a negative one, how do you take it back? You need to have your beta 3 being negative. That's what we are saying. This one should always be negative. Are we together there? I'm repeating this. It's like I'm laboring the point. I'm laboring this point. Why? Because I know as we go down there, when we are actually evaluating our ECM, these are the things that we'll be looking at. Let's look at the coefficient of residuals. Is it negative? Is it significant? If it's like that, we are happy. We know that if there's a shock, our model will be able to go back to equilibrium. That's why I was laboring the point. So let's move on. I'm going to put up the, where is it? Let's have our question. Maybe the question paper will do here. Where is it? It's here. I hope you are. Is it the question paper? No, it's not. Where's your assignment? Oh, yeah. Guys, are you seeing what I'm putting up there, the assignment? Can you see it?
Yes.
So we are now on 3.5. Construct a short run error correction component on your for your model. What is going to correct if there's something? Oh, Lord. Just a second. Okay. Look here. This is called an error correction model. Error correction model. Where is the error here? We are saying we all wish to be at equilibrium all the time, but we won't be there. So if you are not at equilibrium, it means there's an error somewhere, somehow. So how is it going to be corrected? What do you think will correct the error here? Obviously, the error correction term. Which one is the error correction term here? This will be the error correction term. And we know that its coefficient should be negative, should be bounded, right? If it's close to -1, it means the speed of adjustment is fast. If it's close to 0, it means the speed of adjustment is slow. If it's equal to 0, it means there's no adjustment at all, right? So this is actually the error correction term that we've added here. So we are going to look at our error correction term, the coefficient of our residuals. Is it significant? Is it close to 1 or close to 0? Is there a slow adjustment or a fast adjustment? That's what we are going to be doing, right? But before you look at that, you should be able to construct the error correction model. So that's what we want to do. We are now on question 3.5. This is what we are going to do. I'm reading question 3.5. Let's be quick now. Estimate the following short run co-integration equation. Copy and paste your eViews results window in the answer sheet. So this is what we are given. We are given the, maybe I should do this and close this for now. It's better like this. I hope it's visible. Is it visible? Okay, this is this is eViews window. This is the question. The question is saying, estimate the following short run co-integration. Oh no, yes, short run. It's short run. Yes, copy and paste your eViews here. So, what are we given? We have so many things that we need to look at. There's D, LRVAT, that's the dependent variable, and it's the short run one. Why? Because there's a change here. It's actually the change, RVAT. It's the change, can you see that? Then even this one, it's change in LRHCE. This one is a change. This one is a change. But there's inflation, guys. Can you see that our inflation is not differenced? Can you see that? Please listen to me and answer this question. Can you see that inflation is not differenced? Can you see that?
Yes.
But let's go to what we did. When we're checking our inflation here, when we're checking our inflation, this is VAT. In levels, it was not stationary, right? But after differencing once, it became stationary. Can you see that? So in other words, we can say LVAT is of order 1 because it became stationary after differencing once. That's why there you are seeing it, we are having it there under the ECM, right? But looking at inflation, we checked here and it was having 1 star down here. And we said if it's having 1 star, we actually compelled to then move and difference it. But if you look at our lecturers here, they said since it was having the first, when we included trend and intercept, it was stationary at 1% level of significance. But with none, it was stationary, but at 10% level of significance. And we said the overall level of significance that we want to be a bit stricter. It's 5% or 1%. Hence, we moved to difference it. But if you look at your lecturers, they didn't. They are ending here and just assume that it's stationary, it's fine, let's leave it. That's why when we are moving to our ECM, when we are moving to our, sorry for that, when we are moving to our ECM down there, where's my ECM? Down here, inflation, there's no D, because in the, let me say it again. In the error correction model, we put variables that are stationary. So this one we are saying is stationary in levels. This one is stationary after differencing once. This is stationary after differencing once. This is stationary after differencing once. This is stationary after differencing once. So after going through your assignments over and over again, I think because of what I'm seeing here, going up there on your, when you are testing for stationarity, just end here. That's why this part I put it in red. Just end here. We are concluding that inflation is stationary in levels. That's what we are concluding. Though in practice, if it's having 1 star, you need to move on and difference it. So you have to end there. Are we together, guys?
Yes.
Okay,
Yes.
Great.
Yes.
Okay, let's move on. So what are we trying to do now? We want to run an ECM. We are given the variables. So maybe let's do this. We move this one here. So what is it that we are given there? Let me write it here. We have LRVAT. Yes, it's going to be different. We are going to put a D. We have LRHCE. We have LRHYD. We have lab. We have inflation. And lastly, we have res. And in my case, it is res LOV. If you are Simba, it will be res SIM. If you are Ilonga, it will be res IL. Oh, okay, this is what we're having. If you are David, it will be res underscore DAV. So these are the variables that we want to use, right? But if you come here, guys, for those ones who are here last year, I think you saw that I had to make this one real, this one real as well. So this is my real disposable income. This is my real household consumption, expenditure. So we have it already. So here I'm fine because we did that. We did that. So let's now do it. How do we do it? I said the easier way, just know your dependent variable, which is LRVAT. Go to it. There it is. You click on it. You press the control button. The next one, tell me the next one, the next variable.
LRHC.
Yeah, RHC.
This one?
Yes.
Yes. The other one?
Yeah, RHYG. That one.
The other one? Lab. Okay,
Lab.
you can mute. You can mute. I think there's feedback somewhere. You can mute. Okay, there's lab. Then there's inflation. Then there's raise LOV. I'm done with this. So what do? Release the control button. You have to right click, open
as a question.
As a question. Click inside. This is what I have. But what I'm having here is just the ones without the D's. There are no D's if you look at it. But what I'm given here, they should be having D's, the D, right? So I want to put the D's here where there are no D's, right? Where they should be, where we should put the D, let's put a D. So I'm clearing everything here. I'm now doing, so the first one is DL. The first one is D. So I put a D, I open a bracket, then I close it because it's not legged. It's not legged. Can you see that it's not legged? ARVAT is just T, it's for the current period. It's not T minus 1 or T minus 2. So that's why we are closing without putting anything. It's not legged. If you look at this one, it's not legged. Look at the next one, it's not legged. It's in the current period. Look at the lab, it's legged twice. Look at inflation, it's legged twice. Our residuals, it's always legged once. Right? So let's do it. Let's follow what we are given there. The good thing, like what I said, your lecturers, they like us. They always give us even these legs. But in real life, when you're doing it, you should come up with your own legs and justify. Why are you putting 2 legs there instead of 1? Why are you putting 2 legs? You are dealing with quarterly data. Or what's the maximum number of legs that you can put? You are dealing with monthly data. What's the maximum number of legs you can put? You are dealing with yearly. What's the maximum? So usually you see when you're dealing with yearly or quarterly, it's between 2 and 8. Okay, we'll discuss that later. Let's finish what we are doing here. So let's also there's a space there. So let's put the D on the next one. Like this, there's no leg. I'm closing. We go to the next one. The short-run component, there's no leg, just close. We move on now to our lab. The lab, there's a D, but it's legged. It's legged how many times, D?
2 times.
2 times. So let's open a bracket and show it -2. We don't put a T. Yes, here, if you look here, it's written T -2. But when you are inputting e-views, we just put -2. So it's like we are having D, lab, -2, then you close. That's what we want. We are saying the lab is legged twice. So there's this bracket, which is going to be closed by this, right? But after the lab, we know it's legged twice. That's why we are having the brackets there. So that's how I'm gonna put it there. Here. So I'm going to close here, 2 brackets after that. What about inflation? Is inflation difference? It's not, because there we are saying it's stationary in level. That's why it's not difference, but it's legged. How many times? Twice.
Twice.
it's lagged twice. So for inflation, we're gonna put it like, there's no D for inflation, please. So it's just inflation, but it's lagged twice. That's how we put it. Then we move on to the next one, which is the residual. Do we take difference of the residual? Do we take difference, guys?
Yes.
Hmm?
No.
No, for this job. We are only need to leg it once.
Why are we not taking a difference for the residual?
Because it's stationary.
It's stationary level. We tested it, remember. We tested it there when we were doing our long run equation. It was stationary in level and none. And we concluded that there was co-integration. So here you put variables that are stationary. If it's stationary in level, you put it as it is. If stationary are difference in once, you put it as it is, right? So this one, we are not gonna difference it, but it's always legged once, right? So you are done. But you know what, guys? In the exam, don't rush. Because if you miss it here, it means all the other questions we are going to be doing, they'll be wrong. If we miss it here, it means all those other questions up to modeling, they'll be wrong. So what I usually do, let me clear everything. I have to check here and see. I don't want to rush. I don't want to make mistakes. So this is the first one. I'll go and check if it's there. There it is. Don't rush. This is the second one, and it's not legged. I go there, I see it's there. This is the third one. There it is. This is the fourth one, DLab T minus 2. DLab legged twice is there. I go to inflation, T minus 2. There is inflation and it's not differenced. Lastly, res LOV T minus 1. Yes, I have it there. I think I'm happy. Are you happy that side that we have actually captured everything?
Yes.
Then
Yes.
when we do that, we click OK. You're done. Again, I don't want to make mistakes. I don't want to lose a lot of marks there. So I have to be patient. I'm checking again. This is my, sorry, I'm checking again. This is my dependent variable, and I can see it's here. This is my first independent variable. I can see it's here. My other one, not legged, it's here. This one, legged twice, it's here. Inflation, it's here. There's LOV, it's here. And automatically, this one is created. That's the C to be created automatically. That's what I have there. So I'm happy. I'm happy. So I can safely say, this is my ECM. I'm happy. This is my ECM. And the instruction is saying, estimate the following short-run co-integration equation, copy and paste to eViews results window here. So I want to paste it here. So I'm going to copy everything. I'm copying it. Then I paste it here. Maybe to make it look, maybe on the window page, I mean, this is what I'm having. And like what I said, we can't all have the same time here. Hey, let me repeat. And I said it last time. We can't all have 1048 here. We can't. That's what they'll be looking for. And they'll give you a 0. If you're having 1048 there, and how many are we? I think we're over 40 here. We all have 1048 here. All of you get zeros. Because there's no coincidence that you run this ECM at 1048, all of you. you see. So you should be smart. That's what they'll be looking for. So this, guys, let me put it in red, please. Here, 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 here. Be careful. Just run it yourself, because there you'll be in serious trouble. That's what they'll look at. Okay. Even that's why these days they say copy and paste. In 2017-18, they would just say, bring these coefficients. They were just looking for this coefficient. There will be a table for you. They're just looking for this part only. Nowadays, they say, no, people are just doing it once, so they want to check even the time there. Okay, let's move on. Let's move on. Let's move on. The next question. Let me ask you something. Who is there? Ilonga, are you there?
I'm here.
Okay. Why is ECM important? There are two reasons, right? Why is it important? ECM is important. Very important. Why? First reason, it helps in finding the relationships between variables in the short run, right? Right, Lilonga? It will help us to check whether the variables have significant relationships in the short run or not, right? How do you check whether relationships have, why am I asking this? Maybe you are not seeing it or I'm rushing. There's another question. Evaluate the ECM statistically. Also comment on the number of legs included and whether this makes sense in terms of your a priori expectations, right? In terms of theory, does it make sense to have 2 legs on lab, 2 legs on inflation? You are dealing with quarterly data. How many legs should you put when you're dealing when you're dealing with quarterly data? How many legs should you put when you're dealing with yearly data? How many legs should you put when you're dealing with monthly data, right? So what does theory say about that? We'll comment later, but before we go there, I want us to look at this part of the question. At this part of the question, evaluate the ECM statistically. How do you do it? You look at the importance of ECM. And I said the first one is it helps us in finding the relationship between the variables, whether the variables have significant relationships in the short run or not. What do you look at? You look at your T statistics, isn't it? Do you remember that?
Yes.
You go to this is what we are having. Let me leave out the res LOV for now. You check if these variables are individually statistically significant. If they are not, we drop them. We want something that is individually statistically significant. And what is the rule of thumb? Look at the T statistic, right? Look at the T statistic. If the T statistic, let me just use T here, is greater than 2, what do you say? What's the conclusion? Absolute value of 2 actually, not in absolute. So you disregard the negative sign. If the T statistic is greater than 2, what's the conclusion?
It is statistically significant.
Yes, that's what we are now looking at. Let's check our RH. Let's start with the first one. You look at the T statistic. Yes, it's greater than 2. Can you see that? Right? You can look at the next one, this one. It's greater than the absolute value of 2. This one, greater than absolute value of 2, this one greater than the absolute value of 2. But if you want to be specific, you use that one, P is less than alpha, you know that. Alpha is 0.05. So we can say all these ones are individually statistically significant at 1% level of significance, because this one is less than 0.05, this one is less than 0.05, this one is less than 0.05, this one is less than 0.05. So we can safely say all the variables, all the independent variables are statistically significant at 1%, at 1% level of significance. Yeah, that's why you are seeing here, we are going to get this document. That's why you are seeing here, I put this one. Oh, you are not seeing it, and I'm just saying this one. This one. Oh, I made a mistake here. Can you see that? I said all dependent variables. It should be all what?
Independent.
Independent, yeah.
Or independent variables.
Yeah. Imagine we copy each other and everyone is having this same mistake, all dependent variables, and you are the one who is marking. How would you feel? As you can see that people are copying each other, right? So we are saying all independent variables are statistically significant at least 5% level of significance. That's what we are seeing here. That's the importance of ECM. It can actually tell you whether the variables have significant relationship in the short run. So in the short run, we can see that there are significant relationships. In the long run, we also saw that. So we are happy so far. If there's a shock, are we now gonna be able to go back to equilibrium? What do we look at?
The coefficient of beta 3.
Yes. Of which our coefficient of beta 3, or beta 3 in other, oh, let me clear. Here, or let's make it big. This one, so that we see what we are saying. We have to look at this one. It's very important, like what I said. This res LOV. It's important because it's going to tell us two things. The first thing, what is it? Speed of adjustment. But before you look at the speed of adjustment, check at the what? Statistical significance. Statistical significance. How do you check the statistical significance? You look at the T, and we can see that the T here of our LOV is greater than the absolute value of 2. So this one is statistically significant. Can you see that? It is statistically significant.
Yeah, it's less than minus 0.93.
No, minus 0.9, it will help you check the speed of adjustment. Are we together? This is the beta 3. This is the coefficient. Remember, it was beta 3 residuals like this, T minus 1. This beta 3 you are seeing here is this coefficient. The beta 3, yes, is negative. That's what we want. We said it should always be negative, right? If it's positive, it means it will explode. You will not come back to the steady state path of a variable. It has to be negative. Because if it's positive, it means if it's above equilibrium, it will keep on diverging. It will not converge. So it has to be negative, right? So it's negative, we are happy. Is it between -1 and 0? Is it? Yes, it is. Can you see that? And we said if it's close to -1, it means the speed of adjustment is quicker. If there's a shock, you quickly go back to equilibrium. If it's close to 0, it means it's slow in adjusting. If it's equal to 0, it means there's no adjustment. So if you look at our model, so far so good, I'm happy. Because if there's a shock, I know I'll go back to my equilibrium quickly, because it's negative 0.95. So in other words, we are saying 90% of the shock will be dissipated in the next period. So the speed of, so we don't need so many periods for us to go back to the shock, because 95% of that deviation, of that error, will be sorted out in the next period. We'll be moving towards the equilibrium. I hope you're getting it. So here you need to look at two things. You need to comment on the statistical significance of your res LOVE. So if you look at my answers here, we have commented on this one. Let me put in italics. We have commented on this one. I'm saying we should also comment on the res LOV. Are you happy? Oh, it's res underscore LOV. Are you happy with this one? Yes, it is statistically significant. At what percent level of significance? Tell me.
1%.
Why?
95.
P-value is less than 1%.
Yeah, it's actually at 1% using the stricter measure. Because it's actually less than that one, at 1%. At 1% level of significance. Right? What about the other thing? What about the speed of adjustment? How do you comment it? Tell me, I want to type.
The speed of adjustment is quick because it's closer to -1.
It's you. The other one also puts it in their own beautiful English, right? So that you look different. But that's basically that's it. The speed of adjustment tell me it's quick. They're saying it's quick because that's not everyone will write it like this, right? Maybe the other guy would say 95, about, people are different, about 95% of the shock. My spellings, yeah. I don't know, but you can. I wanted. That's why I wanted you to understand the theory, so you find a way of being different, but it mustn't lose sense, right? So this is what we want to write, right? Under the evaluation of the ECM statistically. But there's another thing. But David, I know he's here today. So you are not gonna say, no, we didn't do it. I remember David teaching you this part. Can I ask you a question, guys? Are you there? Let me quickly ask a question before we move on. Why are we not commenting about the coefficients of these ones? Why are we not? we're just concerned with whether they are statistically significant or not. We looked at this one, but not the coefficients. Remember, the answer is this. Remember, these are differenced, but this one is not. So you can comment on this one if you want. Remember, these are difference. So obvious economic theory is differenced away. It will be meaningless, so to speak. So you don't comment on the coefficients of the difference one. You just comment on the statistical significance, right? That's why we do not comment on this one. Then what else should I want? Okay, I want you to say something about this. What is this? Adjusted R squared. What does it say? It's about 6.7%. Can you see that?
Yeah, it's very high.
It's very high because we know the rule of thumb. What is defendable is at least 60%. If it's 60 going up, we are fine. But in real life, you struggle to get something that is like this. If things were as easy as this, we would be millionaires, right?
Yeah, it's clearly showing that the model is fit.
Yeah, the model, so we are saying 60% of the variations in our VAT collections are explained by all these ones. 60% of it, meaning 40% is explained by things that we don't know. There's uncertainty in the world. So at least if the model is giving us an adjusted R squared of 6.7, it's a good model. The rule of thumb, it should be at least 60%, right? So ours here, we are seeing it's ours here, we are seeing it's about 6.7%. So we are saying here, this is how we are going to do it. I'm going to give you this document, but make sure you put it in your flowery English. I'm saying the adjusted R squared is reasonably high, reasonably high. It indicates that about, because this is not exactly 67%, so should be careful here. It indicates that about 67% of the variations in the dependent variable. But because you know your stuff, why are you saying in the dependent variable? You can say about 67% of the variations in the what? You know your dependent variable. You know it, just write it. In the LR VAT is explained by the explanatory variables or by all the 4 explanatory variables, something like that, so that you become different. So it's important to look at your adjusted R squared. What about the legs? Also comment on the number of legs. So usually the rule of thumb, we say, if you're dealing with quarterly data, your legs should be between 2 and 8. So in this case, we can see that, where is it? We can see that this was legged by 2, this by 2. So it's fine, it's fine, it's fine. From theory, we can, if we are dealing with quarterly data, you can leg it, 2 is fine, between 2 and 8 is fine. That's why I said here, the leg length used, seem reasonable, given that we are working with quarterly data. The 2-quarter leg for inflation and LFBs seems reasonable. Okay, it's fine. Let's move on. Let's move on to the diagnostic checks. We do it quickly. Remember, we want to finish by 12. Let's move on to the diagnostic checks. But before we do that, guys, this is very important. You are going to be doing diagnostic checks on the ECM. So ECM is an important equation. We need to save it. Let's not forget to save it. You try to close it here. You name it. You can leave it as equation 2, but I don't want to confuse myself. Let me just save it as ECM. Then I'll say, okay, you can see that here I now have my ECM. Can you see it? Here. And now I have the ECM. And I mustn't forget to save even this wake file. I have to save it, constantly save your wake. So I'm done. I'm done here. So what I'm going to do, guys, for those ones who are using eViews 10, I'm not sure if this will work on eViews 8. For those ones who are using eViews 10, I will also send you this wake file. So you'll be having this. So I also send you this wake file, right? Now when you are doing your work, you can also open this one and try to play around with it. But I'm not encouraging you to be lazy. Because if I send you this wake file and your name is, let me just mention it in passing. Your name is Alvina. Alvina, are you there? Alvina? Yeah, so
Yes,
if I send you this wake file and your name is Alvina, you just go to your res, because you are not LOV, it will start with what? You go to rename here. Then it will be L what here? You are Alvina, L. Is it like this?
Yes, it's like that.
So she's done. Can you see that? So going forward, where they are looking for, yeah, they're saying use this, you are fine. It's changed there. But let's go back to where we were. I'm not encouraging you to be at, sometimes we need to do those things. Okay. This is what we are having. Let's move on to diagnostic checks. This you did.
Sorry, Mr. Tende, sorry to interject there. If I'm using I'm on eViews 8, will this be able to help me as well?
I don't think EVS will read what is coming from eViews 10. I'm not sure. I'm not sure.
Okay.
But I know you,
All
you
right.
know how to do it, so you don't need even this wake file.
I'll try. Thanks.
Sharp, sharp. But the answers will be there. Don't worry. I will discuss some stuff when we're done. We'll stop the recording. We'll discuss. Okay. This is what we are having, right? So we want to perform diagnostic checks on the ECM. We want to perform diagnostic checks. What? So it was like this. I think you saw it. It was like this, guys. Here, that's the question. Perform diagnostic checks on the ECM. So don't make a mistake and you click on equation 1, because we want to perform some checks on our error correction model, right? Test only for potential problems indicated below. There are so many problems. I think you did some stuff with David. Was it OLS assumptions? No serial correlation, no heteroscedasticity, no misspecification, no multiple linearity. I think you remember those other things. We are now performing, we're now checking if they are there or not. If they are there, it means we are violating some stuff. So it's not a good model. A good model should not violate the assumptions. We are building a model obviously based on some assumptions. So we have our model, we have our own ways of doing interpretations. But if that model is violating the assumptions, so using the model, the classical linear regression model, it means we are wasting time. It mustn't violate the assumptions if it's a good model. So look here, we've been ticking a lot of boxes here. We tested for stationarity. Remember, we said the underlying assumption is variables are stationary. We tested for stationarity. They were not stationary in level, but most of them, they became stationary after differencing. Once we were happy, we ticked a box. Then we said, let's check out if there is long run relationships. Do they exist? Then we checked and we concluded that there was indeed co-integration. We ticked that box. We were happy. Then we said, it's good to know about the long run, but we should also know about what is happening in the short run. When there's a shock, because usually we live in the short run, right? Not in the long run. If there's a shock, we'll be able to move close to what it will be in perfect world, right? In the equilibrium. Then we checked that. And generally, we were happy because even our R squared, it was defendable. It was above 6%. Even the legs that we used, we said we are fine with it. We even checked our res LOV, the speed of adjustment, we are fine with it. We even checked if it's statistically significant or not, and it was significant. We were fine with it. We ticked that box. So we've been ticking a lot of boxes, but we are not yet done. Now we find, let's check if this model we have been doing is not violating the assumptions. So if it's violating assumptions and we are not happy, it means we'll end there. We cannot use this model to help us in predicting the future. We end there. So econometrics is not easy in real world. You'll be doing a whole lot of models, running regressions, discarding them. And you come up with a good model, right? And they sell those models to say, if the all-share price index is like this, it's affected by A, B, C, D. If the indices are like this, the Johannesburg all-share price index will be like this. So if you can build a good model, you have so many clients. They'll come to you to say, no, this guy, his model, it's close. This guy doesn't miss. But coming up with a good model is very difficult. We are living in a world that is uncertain. There are some other factors that we don't even know. But those factors, they affect our dependent variables. They affect Johannesburg all-share price index. But you want to come up with a model that will help you predict and make money, but it's difficult. So in econometrics, you keep on doing stuff. You have to know theory first before you run these models. Okay, we have been ticking boxes. Let's push quickly. We are about to finish. So we want to test for normality. We want to test for serial correlation. We want to test for heteroscedasticity. So how do we do it? To make our life easier, you need to just have a table. That's why I came up with this table. These days, they're not even giving you these tables, these guys. So this is a table. You've got your Gujarati, you know how to test for normality. You use the Jacob-Bera test. How do you test for serial correlation? There are so many ways of doing that, but we're going to be using let me annotate for you to see. We're going to be using, I'm saying for normality, we are going to use the Jacob-Bera test. For serial correlation, we're going to use these two, the Lungbox Q and the Bresch-Godfrey LM test, right? Then for heteroscedasticity, we also have two. We're going to use the ARC LM as well as the white, right? This is to do with the residuals. We are testing residuals, right? Residuals are very important when it comes to OLS. We are going to check the residuals, okay? I'm repeating for a reason. So let's start with let's do it quickly. Let's start with our normality tests. What is the null hypothesis? This is different from what we've been doing. If you remember, under co-integration, the null hypothesis was no co-integration. Right? Then the alternative was there is co-integration, right? That's what we've been doing up there. If the other one, I think for stationarity, the now hypothesis was not stationary or non-stationary. Ne? The alternative was there is stationarity, right? But it's different from ECM. ECM is the other way around. The now hypothesis, we write what we wish to see. We write what we wish to see. We write what we wish to see. Residuals are normally distributed. There is no correlation. There's no serial correlation. There's no heteroscedasticity. That's what we write under ECM only. It's the other way around. When you're formulating your now hypothesis in all other stuff, you make sure that the now hypothesis, you write things that you don't want there. That's your now. But under ECM, we write what we want to have. That's the difference. Only for ECM. That's why we are having here normally distributed. No serial correlation, and lastly, no heteroscedasticity. So this part you have to write it. You'll be having it, it's a template, you'll be having it. So let's go straight to it. So what about the rule of thumb? Before we go to it, we are going to spend 5 minutes here. The rule of thumb, if P is less than alpha, our alpha we are going to use is 5%. If the probability is less than 5%, reject the now hypothesis. If P is less than 5%, reject the now. So let's do it. We are starting with, I've opened the ECM. This is the ECM. You go to view. What do we want to do here? We want to do residual diagnostics. It's to do with the residual, the error term. So we go to residual diagnostics. Which one are we looking for?
We are looking for normality.
Normality, it's here. That's the normality.
Yes, normality test.
Then you click, right? Then here, what is the JB statistic? I can see the JB is here. Let me quickly encircle it. This is the JB statistic. This is the probability or the p-value. So coming to here, the JB statistic, it's 99.60190. Then the p-value is 0.0000 like this. So tell me the conclusion. Should I reject or not?
Yes, you have to reject the residual.
You have to
Are not
reject
normally distributed.
under 5%.
So we say reject H naught. I will write it like this, it's fine. Meaning what? You just meaning
Yes.
residuals
are not normally distributed.
are not normally distributed. Done. We move on to the next one, which is serial correlation, Lungbox Q. Right? I'm still there. It is still ECM. I just click on view. We go to residual diagnostics. We're looking for Lungbox Q. Lungbox Q. So which one should we take there?
The first one.
The first one. Others, are we together?
Yes.
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 So we take the Q. Okay. If you look at this one, we need to give it some legs there. So usually the legs that we use, we test for serial regulation up to the 6th leg. So when I click there, it's showing me, I think you are seeing it, let me encircle it. It's showing me 36. But what I want usually is up to the 6th leg. We test up to the 6th leg. So I have to change there. Can you see that? I have to change here and put 6, right? We click OK. If you look here, I have how many legs? 1, 2, 3, 4, 5, 6. Are you seeing that, guys?
Yes.
So I have
Yes.
1 to up to 6. So what is my Q statistic on the 6th leg? What is my probability? That's what I'm looking for there, right? So this one I can do copy and paste. I can do copy and paste. I'm copying my Q, copy. I paste it here. Then the P value, I copy, I paste it here. What is the conclusion?
We rejected the HO.
We reject HO, meaning what? There is
no serial. There is serial correlation.
meaning there is, right?
There is serial correlation.
Yeah, we are going, I think, to learn more about the Lungbox Q, the Bresh Godfrey. I think you should read some stuff from Gujarati to say what is it testing. That's where you see that if you are doing Lungbox Q, you're actually looking at the first order serial correlation. So you also need to maybe read some part in Gujarati, right? So here we are saying it's like this. What about the Bresh Godfrey? We go to residuals. Bresh Godfrey, which one? LM. So I'm
Yes.
going to this one. How many legs? There are 2. I click on OK. But here, I want to show you something. This one is the observed R squared. That's the observed R squared. That's what you are seeing there. The N R squared is the observed R squared. So going to our E-views, let's look for observed R squared. This is actually the T statistic, and this is the probability, right? So we are going to take this, that's the observed R squared. Then we are going to take the probability. What are you saying here? What's your conclusion? What's the conclusion?
We are not rejecting.
We are
So-
failed to reject.
So we failed to reject. Meaning what?
There is serial correlation.
There is
No,
If you-
se-
no serial if you
there
reject.
is no serial correlation.
There is no serial relation.
Okay. Then lastly, let's test for heteroscedasticity. We look at arc LM. We go to residuals. This is heteroscedasticity. Arc is this one, or arch or arc. The observed R squared, the legs is 1. I'm not changing anything there. I just click there, observed. I copy here. That's the observed. We paste it here. What about the P? What's your conclusion?
We fail to reject.
We failed to reject,
Fail.
right?
Yeah,
Yes.
it failed.
Yes.
There is no heteros.
Yeah, finish it. Know what?
Heteroscedasticity.
Yes,
There
finish
is
it.
no heteroscedasticity.
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 Yes, that one. There's no that one. So there's what? If there's no heteroscedasticity, it means there is homoscedasticity, right? It means there's homoscedasticity. It's fine. Let's go to white. Heteroscedasticity. Where's white? There. But look here. We do not want to include the white cross terms. We want to test it in the strictest sense. So we do not include no CTE. Here it's important because you may lose marks. Here we are saying we test no CT, but here we are saying the CT includes CT. So you need to untick, isn't it?
Yes.
We have to untick there. No CT. Then, okay, observed is that one. I copy, I paste it here. We copy the probability. I paste it there. What's your conclusion?
To reject again.
We fail to reject, eh?
Yeah. There is no heteros.
Yeah, there's no that one.
There's no that one.
Yeah. Okay, fine. So what's your conclusion? Is this a good model? A model that is violating some assumptions, and the serial correlation assumption is an important assumption. It is violating it. Is it a good model? Here you are saying there is. Here you are saying there is serial correlation. This one, yes, but we can talk about it, but it's not much of a problem. Here you are saying there is one of the tests showing that it is there. So is it a good model?
No.
Yes, it's fine on a heteroscedasticity, but on serial correlation, it should not show serial correlation. But you know what? In your assignment, they were not asking you about this. That's why the lecturer had to move to the model. But in real world, if you see a model like this, you end here. Sorry, my bro or my sister, go back and try to play around with your variables so that it will not violate the assumptions. But he's not saying evaluate here. That's why we are not saying anything about this. We are moving straight to the model. Are we together?
Yes.
Okay. But this model,
Yes.
what is violating that ish. Let's leave it. Let's move on to the last question. Create a model statement in eViews to combine long run and ECM. Provide your model statement, copy and paste. And what? And copy of a graph depicting actual and modeled. Oh, let me quickly explain something here. Let me quickly explain something quickly. Quickly, so that when we are running there, it's easy. Just a second. Oh, but we don't need it. Okay, I can explain here. We now want to come with a model. Look, let's say we have our VAT. This VAT is on Excel. This is the data that you are given, right? Then after coming up with our model and everything, let me put figures. They're coming from my head. Let's say this is 250, this is 289, maybe that we are now in 320 or 345, now 370. This is actual. Let me change the color. Guys, are you there?
Yes, sir.
This is actual. Something that you are seeing there, if you check your eViews. Then you guys, we have your model. That was VAT. You guys were coming up with a model. You are telling us that VAT depends on, it was depending on what? HCE, I think it was also depending on what? NY, all those other things. It's you who's telling us, right? You remember those are those variables. Then after estimating everything, you are going to come up with an estimate with something, right? We have estimated. This is an estimate. That's why I'm putting a head VAT hat. This is just this is an estimate or a modeled. This is an estimate or a modeled, right? After coming up with, we are using this. After coming up with everything, these are the figures we are getting. Can you see that there's a difference between the actual and the modeled? Can you see that?
Yes.
If it's a good model, a perfect model, where the R squared is equal to 100%, it means the modeled and the actual, there will be same figures. If it's a perfect model, it means even here we have the 250, 289. Are we together? Yeah. Are you getting me? If it's a perfect model, but hey, you won't get a perfect model, right? It's difficult to get a perfect model. Okay, so I don't want this. Oh Lord, I don't want this part, because we know we are not gonna come up with a perfect model. So this part, forget about this part. This is what we are having modeled. So there are some differences. Can you see that? So if you plot a graph of the actual, so for actual, I'm going to use black. Let's say the actual is moving like this. Then your modeled, let me use red. Let's say your modeled is moving like this. Can you say your model is good? It's not, ne? It's not close to the actual. But if your model is moving like this, maybe it's missing a bit like this, you can actually see on the graph that it's not exactly the same, but it's close. It's a good model. You can actually show it on the graph. Are we together?
Yes.
This
Yes.
is what we want to do on modeling. This is what we want to do on modeling. So what we are trying to do here is to come up with a graph. To come up with a graph, right? Here there's time. Maybe here it's amount. To see what will happen with the VAT, maybe this is the actual. Maybe it will be L, just VAT, this is actual. Then we want to have maybe something that will move like this. This will be our modeled. So if you write it as VAT underscore 0. That's what we want to come up with here. Are we together?
Yes.
But there's a
Yes.
question, look, our model, we are now having something that is differenced. But if you look at what is in Excel, those ones are in level, they are not differenced. So our model, we're working with differenced variables. So we need to go back to levels. Are we together? Let's go back to levels so that we'll be able to compare this in levels versus this in levels. Are we together? That's our task. So we just need 3 steps. Moving from the difference, going to the levels, then we compare. That's what we are doing. So let's go straight to it. I hope you're getting it. Maybe for now, let me maximize e-views. This is the e-views we are having. So what I'm trying to say is, we want to come up with a model. So if you're coming up with a model, you are simply saying, there are 3 steps here, guys, please follow. We want to come up with a model. But where is it coming from, the model? You should know, because we are told here, let me do this. I hope you will be able to see it. What are they saying here? On question 3, they are saying create a model statement in eViews to combine. What are we combining? Equation 01 and our what? ECM. So the model is coming from equation 01 and ECM. That's why I was saying save your equations. The model is going to come from equation 01 and the ECM. Are you still there, guys?
Yes.
Yes.
Great. If you're still there. So let's do it. So our model is like this. It's going to come from equation 1 as well as from ECM, right? So we just need to take equations from here and equation from there. So if this is 1 and if this is 2, I need to have equation 1. I need to have equation 2, which is my ECM. But we know that ECM, the data, the variables are differenced. Are we together? So lastly, I need to remove the differences. How do you remove the difference? You need to take what? Exponent of the logged one. After removing the difference, take the exponent of the logged one. That's what we want to do. And we are done. This is what we are going to do, right? So let's do it. I need to have 3 windows here, but I will explain more maybe after this assignment about the model statement because we'll need it going forward. What I want us to do here is to have a model. So I want to have 3 windows. How do we come up with a model? Oh, do I know? We go to object. Want to come up with a new object, right? We go to object, new object. Do you want an equation? No. A vector, a graph. Where's model? Here. We want to come up with a model. It's untitled, it's fine, no problem, even without a name. Just click like this. This is my model. So look, guys, I'm trying to write something here. I'm clicking my keyboard, but I can't do anything. So please don't think it's your eViews. You need to go to text here. If you click on text here, you are enabling this. You can now type, right? If you don't click on text, you'll be in trouble. So it's like I'm having my model. Let me put my model here, right? And I also need to open equation 1. But I need an equation. If I go to view here, if I say representations, I'll be able to view this equation. This is the equation that I want. So I'm going to copy this equation. I'm going to copy this equation. That's the first thing I need on my model. Remember, we need equation 1, we need ECM, then the third part, we need to get rid of the logs. So this one is done. I can even close my equation 1. I need to open ECM. I view representations because I want to copy this part. That's the second one I need. I have to space. I can even close this one. Let me maximize my model. Let me maximize my model. So this is what I have. So the last part, I want to remove the logs. Okay, we'll go to that. So the first thing that we need to do, I'm gonna write so that you will not lose me here. The first thing that I need to do, it's like I'm given L R VAT, I'm taking from equation 1, is equal to what was this part you are seeing here is what was estimated. So in other words, this is L R VAT with a head, it's an estimate, plus the residuals, obvious. That's what you are seeing here. That's the first part. So what we want to do is to make this subject to the formula. I want to have u, this residuals is equal to, if I take this one to the left side, it will change the sign to as positive, it will be negative. So I'll be like having AOR VAT minus AOR VAT, sorry, with a head. That's what we want to do. So I don't want to confuse you here. So I want to have something like this. My residuals is called res LOV. Here they'll catch you. If your name is ILV, it will be res LOV. So I want to have something like res LOV is equal to LRVAT minus everything here that you are seeing. That's my first equation. That's what I'm gonna do now. Oh, because of time, I'll quickly do it. I'll send it to you, but we need like maybe an hour next time for me to discuss this with you. Where is it coming from? Why are we doing this? So that you not mistakes. You will not make mistakes when you are doing this. So myself, I don't want to type things a lot. I know where my res LOV is. I'm gonna copy it from there. There, I want to copy it. I want it to be the first one here. We should be equal to. Then the other equal sign should disappear. Minus everything should be in brackets. It's like here I'm having res LOV. This thing that is in brackets is LRVAT hat. I hope you've seen it. It's fine. We'll need more time on this. Then I'll be done. Then the other thing that I need to do here is to remove the differences. I want to remove the differences. That's the other thing. How do we remove the differences? How do we do it? This I have to show you. I know there's no time, but I have to show you. Let's say, guys, you are having something like this. DLRVAT. This is a difference. This is actually change in LRVAT. This you now know. What is change in LRVAT? Let me write it down here. Sorry for that. The space. I'm saying, what is DLRVAT? This is the same as change
Okay, bye.
in LRVAT for this period. Let me put the T's maybe for you to see. Is equal to LRVAT of this period minus LRVAT of last period. This we did. This is the change. We started with this. This is the change in LRVAT. We did this, right? Now we want to remove the D. But how do you remove the D? In other words, we are having D, this part. LRVAT is equal to LRVAT of the current period minus LRVAT of the previous period. We want to make this one subject to the formula. In other words, we have removed the D. How do we make this one subject to the formula? I will take this one to the other side. Are you seeing it?
Yeah.
So I have LRVAT is equal to D LRVAT. It was negative, so it will be plus LRVAT T minus 1. That's how you remove the D's. So playing around with this, you are clever because you need this one. How do you get the one without a D? You want to remove the D. Take the one with a D. At the end of it, just add LRVAT, but it should be legged once. That's what we want to do. So how do we do it? I'm gonna go here. I'm saying for you, we are saying here, for you to get the one without a D, I can literally delete the D's here. I'm removing the D here, the D here. Then at the end, we are saying just add this variable, just add the variable at the end, but it should be legged once. You would have removed the D. I don't want to see people who go like what other students were doing last year. We are saying, let's remove the D's. They are going literally in this equation and deleting where there's a D. They were deleting these things. There's a D there, they are deleting that. No, you don't do that. Just add this one at the end, legged ones. You would have removed the D. So you are done with this part. The last part, we are now removing the logs. We have LR VAT. We want to remove the logs of this. How do you remove a log? You take an antilog of it. How do you take an antilog? You use exponent, right? Exponent. So if you do this, it means you would have removed this L. We have, next week, we need to have this class. I'll show you how to do it after you've submitted your work, but this is correct for now. Next week, we are going to do it. When you're done with this, you just go to, I think there's solve somewhere here.
Oh.
Then you just say, yes, you want to modify, it's deterministic, no longer stochastic. Then you click on OK. It's done. If it's like this, it's a thing that is done. You go back to text. This is what they said, copy and paste. They said copy and paste in the space provided. I'm going to do that. I'm going to also share with you the Word document so that you'll be in a position to see. So this part you are going to take it as it is from me. This is the part, provide your model statement, just 3 marks. So we are copying and we have to paste it here. But let me put it in, let me see. Yeah, it's now, but it's fine. Let me put it maybe in a, I don't know, maybe it will look nice. Let me put it in maybe all borders. Yeah, something like this. This is our model statement, right? Then the other part, they are saying we are about to finish. The other part, they are saying a copy of a graph depicting actual and modeled. I said you shall see that your actual VAT will be there. You're also going to have the modeled, but it will be having an underscore and 0. So after solving the model, we should be in a position to see that. So if I maximize this and I try to close the model, let me save this model. I'll need it. I'll click, I will also have to save stuff here. I can see that the model is now there. I've saved the model. And indeed, I can see, where's my VAT? Here.
At the bottom.
The one with the 0 is the modeled. And this one is the one from Excel, right? This is the modeled. So we want to see if they are close to each other. If they are close here, we say, at least our model is good. So that's what we are doing. How do we open them? You click on this one and the other one that is modeled. You open as group, not as equation, but as group. Look, we have lost some numbers here. Why? Because we're using legs, we're legging. So obvious, for 1990, you will not be able to find that one because it's like legged. That's why we are losing some numbers. Don't worry about that. So you go to view, you go to graph. Next week, we are going to do this in detail in class. You click on OK. This is the graph. The blue one is the actual. The red one I can see is the modeled? Or is the other way around? Okay, yes, it's the other way around. So we copy this, they want this graph, we paste it here. That was the graph. So I think we'll be done with the assignment. Thank you so much for joining me. Let me stop the recording and we talk something.